Right. Okay, last time, let's review. Last time, we had our big sort of 4,000 year, roughly, this is 2000 AD, CE. This is 2000 BC. We were talking about the Babylonians. We went over this YBC 7289. We went over Plimpton. We knew that these, the Babylonians, these are Babylonians. Babylonians knew the Pythagorean theorem. Pythagorean theorem long before Pythagoras and the Pythagoreans. The Pythagoreans are around here, 550 BC. I want to tell you about some other things that you would see. And the Pythagorean theorem, by the way, it's not like it was discovered by the Babylonians and then handed down. It was discovered all over the place. In India and China, there's evidence throughout time. The Persians, for all we know, the Mayans knew the Pythagorean theorem, and they didn't record it in a way that survived to today. So let's talk. So we talked a little bit about the Babylonian, Mesopotamians. Let's talk a little bit about the Egyptians. So there are the two most famous. We talked about YBC, and the other one was Plimpton. Plimpton 322. These are the kind of, there's thousands of them, but YBC and Plimpton are the two kind of largest, best studied among the best studied clay tablets from the Mesopotamian Babylonian tradition. For the Egyptian tradition, there are two things. One is called the Rhynd. Anybody know what they're called? This goes to the question of, should you do the reading before or after? Anybody know what the two big Egyptian papyri are called? Yeah, it's cheating because you actually know this stuff. Go ahead, Cindy. The Rhynd papyrus. Okay, great. There's the Rhynd papyrus, and the other one's the Moscow papyrus. And the Moscow, these are like the two biggest ones. The Moscow one is in Moscow. The Rhynd one is in the British Museum. Exactly right. The British Museum. And so I have the Rhynd papyrus right here. So this is, Cindy will know better than me. This is a hieroglyph. It's got all kinds of mathematical things in it. There are some very interesting aspects to this. Again, they're kind of all in the elementary, what today is elementary math. Before that, there was, this is maybe an apocryphal story, but apparently Egyptian carpenters would have on their truck a loop of rope. So you would carry a loop of rope, and that rope would have 12 equally spaced knots on it. 12 equally spaced knots. Does anyone know why? Why? How do you get right angles out of a loop of rope with 12 equally spaced knots? How? Bingo. Bingo. So check this out. If you make, so this is length 1, 2, 3 with the knots here, they're equally spaced. So that's 1, 2, 3, 4 knots. And then 1, 2, 3, 4, 1, 2, 3, 4. And then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That is 4 plus 4 more is 8 plus 4 more is 12. That's 12 equally spaced knots on a loop of rope that form a 3, 4, 5 triangle. And if you take this rope and you have a guy standing here and you measure out 4 of those knots, and somebody else measures out where distance 3 or distance 5 away are, and you pull that rope taut, that will give you a right angle. That's how you get a right angle in ancient Egypt if you're a carpenter. This is like apparently their standard method. By the way, let me say one more thing. When I say things like this, I've read them places, I've heard them, I've talked to people about them. For all we know today, we know much more about what really happened. And if any of you go, however you find a piece of information that I have given you that is not true or no, or there's now new evidence against it, you get, let's say 5, maybe that's too generous, between 2 and 5 extra credit points for finding something and contradicting me. So please do this. Please actually like investigate anything that I say. It would be awesome to have you come and say, hey, Professor Kontorovich, I looked up this thing that you told us, and here's ideally the primary source, the primary evidence for why it's not exactly how you said it, and you'll get extra credit. This is how I learn this stuff, is people come and they correct me, okay? So like I said, mathematics is eternal truths. What we know about the history, I'm constantly learning. So as far as I know, this is how the Egyptians apparently were using the rope. There's something very interesting about this. Is this the Pythagorean theorem? This is very subtle. What is the Pythagorean theorem? Yes, if you have a triangle which is right, then a squared plus b squared equals c squared. That's the Pythagorean theorem. What's this? The converse, the other way around. The other way around is also true, is also a theorem, and that's actually what the Egyptians supposedly were using to get right angles. The converse Pythagorean theorem says if you have a triangle with a squared plus b squared equals c squared, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, which is 5 squared. That's why 3, 4, 5 satisfies that relationship. Then the triangle they form is right. It's a very, very important and subtle, not so subtle, actually. It's a huge gap between the Pythagorean theorem and its converse. And they're actually using the converse of the Pythagorean theorem to get their right angle. So that's a cool little vignette about a piece of Egyptian mathematics. The Rhynd papyrus works out all kinds of other problems. So does anybody know what a vinculum is? Have you heard of this word? Vinculum? You use it all the time. Yeah. Great. If you have a repeating decimal, that bar is a vinculum. Okay, this means 0.2345345345 forever. How about anybody remember complex conjugation? If you have a complex number 1 plus 2i, what's its conjugate? It's okay if you don't remember. Anybody remember? Its conjugate is 1 minus 2i. Does that ring a bell somewhere way in the back? What's this symbol on top? Vinculum. If you write the square root of 25 plus 3, what's this part of it? Vinculum. Okay, you use vinculums all the time. It's a way of grouping things. It's not as good as parentheses. Like if I want to write an entire sentence, I can put that in parenthesis. Imagine I had to draw a line over top of that entire sentence to make sure you know it was parenthetical. So we use now parentheses much more, but we are all over the place are using vincula for things. When you write, so this is a little subtle. This is where I'm going out on a limb. When you write 7/12, what is this bar? I claim it's a vinculum. I don't know that other people would agree with me. In fact, this is an opportunity for you to get some extra credit points. I claim it's a vinculum, and I claim that because what the ancient Egyptians were doing is they would have, like, this is the symbol for 3. Not too shocking that was their symbol for 3. They had a kind of vinculum. It was a hieroglyph that looked like that. And what would this mean? Yes, 1/3. This is how they notated 1/3, is with a hieroglyph that is I don't know if there's any, so this is a question for the historians, is there an actual train that goes from the Egyptian hieroglyph to the modern vinculum? Tell me if that's true or not. But the Egyptians, because they had this is an instance of how we communicate mathematics turning into mathematics. So because they had a way of notating 1 over something, all of their problems became, how do you express? So this is called Egyptian fractions, Egyptian or unit fractions. Unit fractions is expressing whatever you want to express, expressing fractional fractions, let's call them fractions, using only unit fractions. Unit fractions are fractions where the numerator is 1. Unit fractions means numerator is 1. And if the numerator is 1, you don't have to put it. If the numerator is always 1, you just put a vinculum there, and you get 1 over the number. So here's a typical, this is something that's actually in the Rhynd papyrus. I don't know where in here, and this is only a fragment of it, so I don't know where in here this problem is, but here's the kind of problem that they were solving. So here's a problem. A job pays, a carpentry job or something pays 5 loaves of bread, 5 loaves, but 8 guys show up. 8 workers come. 8 workers do it. How to split? How do you split those 5 loaves of bread into 8 workers? Okay, so here's 5 loaves of bread. Well, if you had pizza, you would cut it into 8 slices. And everybody gets 5 slices, right? That's 5/8. 5 slices each. 5 slices. Each slice is 1/8 of a pie each. They didn't like this method, especially if you go to something more complicated than 5/8. You have to chop up. Anytime you chop, it's not precise. You can't quite see what 8ths are, what's a good way of sharing these 5. So they came up with a different method. And the question is, how do you express 5/8 in terms of unit fractions? So here's what they would do. Does anybody know? Or you want a minute to think about it? Let me give you a minute to think about this. Talk to your neighbor. See if you can figure out a better way to split up 5 pies, 5 loaves of bread, among 8 people in a way that will have as large a piece for everybody as possible. You can talk. Yeah. Talk. Find somebody, sit next to somebody, argue. Keep going. So close. Tell me again. Jemima, thank you. Can we hear Jemima, guys? You got it.
I said split the first 4 into halves, and then the last one you split them up.
5/8 is 4/8, which we would call a half, plus an extra 1/8. There's no reason to split the first 4 pies into 8 pieces. Split them in half. Everybody gets a nice half. And then the last pie, you split into 8s, and you get an extra slice of that. So the fact that 5/8 is 4/8 plus 1/8, a half plus an 1/8, is what the Rhynd papyrus says is the correct way, is the better way to share those 5 pies among the 8 workers. Everybody see that? So this is again, this is something that you wouldn't even dare say next door because it's such an utter triviality about how do you express fractions in terms of unit fractions. But actually, Once you start asking these kinds of questions, they lead to real deep mathematics. So this is something called, this is a problem of Erdős. Anybody heard of Paul Erdős? We're going to hear a lot about Erdős. He's a very famous mathematician from the 20th century. Erdos-Straus. Erdös-Straus observed that it looks like for all numbers n, for all natural numbers n, at least 2. Is everybody okay with these symbols? This symbol means for all. This symbol means for all. Again, mathematicians are obsessed with compactifying ideas so that you get right to the, you'll get used to the for all and there exists. For all integers n at least 2, there exist, this is there exist, or there exists, depending on how many things. We have integers x, y, and z in the natural numbers. So we're going to learn how to write math speak. This symbol is an element of. This symbol, this bold n, is the natural numbers. Natural numbers. Depending on whether you're French or English, you start with 0 or you start with 1. So these are the whole numbers, the counting numbers. Maybe 0 is included, maybe not. For me, 0 is included. I think that makes me French, which it's the only time I can be considered that. So for any number n, for any natural number n at least 2, there exist whole numbers x, y, and z so that the number 4 over n is equal to 1 over x plus 1 over y plus 1 over z, unit fractions. Can the fraction 4 over n always be expressed as a sum of 3 unit fractions? So let's just do an example. Somebody give me a number n. 17. Well, you're really working me. All right. 4 over 17. How are we going to express 4 over 17 as a sum of 3 unit fractions? Can we do it? 4 over 17 smells like, God, I don't even know where to start. You want to take a minute and work on this? Take a minute and work on this. Try to figure out 3 whole numbers that you can add the unit fractions of those 3 whole numbers and make 417. And I will ask GPT or something. Oh, I'm not logged in here. Write 417 as a sum of 3 unit fractions. Ha. There's an algorithm. It's not great. You gave me a really good one. 17 is a hard one. I think in the interest of time, let's add this to your homework. Yeah. 17 is a really good one because a lot of the early ones you can really you can pretty quickly see how to do it. 17 is a really good one. By the way, there's also a question of whether you want to use distinct unit fractions, whether x, y, and z need to be different numbers. So let's not formally add this to your homework, but as an exercise for any of you who want to play with this at home, how can you write 4/17? You see, it's not trivial. It's not just immediately obvious how you're going to write 4/17 as a sum of 3 unit fractions. And in fact, it's so not trivial that this problem is still open today. This is the Erdos-Straus conjecture. Something people have been working on. I think it was stated in something like 1948. I mean, stated in this modern form. Of course, it's inspired by the Egyptian notion of fractions. Allison. Sure. Give me another one. Okay, 8 is a good one. 4/8 is a half. A half is a quarter, an eighth plus an eighth plus a quarter. They can be the same if you really want them to. If you really want them not to be the same, there's a trick. The trick is that if you have things that are the same, you can always break them up because a half plus a third plus a sixth is 1. And so if you're ever trying to make 1, you use this to play around and give yourself something that's not an eighth plus a quarter. Okay, so the integers 4, 8, 8 for x, y, and z, this is for x, y, and z, solve the sum of three Egyptian fractions problem in the case of n equals 8. Okay, does that make sense? And the question is, how do we solve it for n equals 17? The question is about natural numbers. The question is about for all natural numbers. Yeah, I guess I didn't say what n is. So n, Erdos had a famous saying, n is a number. In fact, there's a movie called N is a Number, I think. It's a documentary about the life of Paul Erdős. Very fascinating guy. Yes, natural numbers. Whole numbers. Natural number. Okay? So the exercise, should you choose to play with it, is can you do it for n equals 17? Here's the case. Let me make this a little bit easier to read. Here's the case n equals 8. We solved x, y, and z if x is 4 and y is 8 and z is 8. And here's a trick to disambiguate those if you really need to. Okay? And this conjecture, despite all of the big brains in the world that have ever thought about this, and there have been very many, this is still unknown today. This is an open problem in mathematics. You solve this problem, you'll be very famous. This is something a lot of people have worked on and thought about. Show that for every single, is it true that for every, you could solve it the other way too. You could show that it's not true. You could find you'd have to go really, really high. I think this has been verified numerically up to 10 to the 20 or something. Show that for every possible denominator here, if you want to write 4 over that denominator as a sum of 3 unit fractions, that it can always be done. Unknown problem in the 21st century in mathematics, despite everything we know. Okay, so this is just an instance of how the fact that we know some things, that we have some theorems. Every time you have a theorem, every time you have an idea, it's a miracle. We do not have a right to knowledge. And this is an instance of just how impotent mathematics is in the face of something this simple, this trivial. And also how an idea as trivial as they didn't have a way of going from a vinculum to mean a reciprocal to then putting a numerator there, and now we have fractions. It took us a long time to get to writing 7/12. So it's an instance of the restrictions placed upon you for how you communicate, leading to actually deep mathematical problems or discoveries. Yes, don't tell me, Sanjay.
Could this conjecture ever become a theorem? Because in theory, it's like infinity, and how would you check all of this?
Excellent, excellent question. So the first thing you might want to do is check it for all n, but there's infinitely many n. So that is why mathematics, we're going to get to that in just a little bit, does not rely on computation. This is the difference between computation and mathematical rigorous proof. There are infinitely many right triangles. And we are not going to check for every possible right triangle that the sums of the squares of the two sides is equal to the square of the hypotenuse. We're going to prove once and for all that for all possible right triangles, all infinitely many of them, all uncountably many of them, we'll get to accountability. This equation always holds. So that's the beauty of rigorous mathematical proof. It's not just something where you establish it once in a particular instance and then say, okay, we're done. We want to, the only way this problem will be solved is not by computation, but by argument. That's a really, really important point. Great question. Other questions? Okay, I think that's all I wanted to say about, there's a ton, we could spend an entire semester just talking about the Babylonians. We could spend an entire semester just talking about the Egyptians. I want to get to other stuff. Let me make sure that I'm not missing anything. All right, very good. So let's go straight into Sanjay's point. Remember in YBC, in this 7289 or whatever, we computed, or this student computed square root of 2 to an accuracy of 10 to the minus 6, right? So we got 6 decimal places, right? That is an accuracy. I would say that this is a pre-mathematical, but this is past engineering, post-engineering, but pre-mathematics result. It's a computation, but it's a computation so precise. The reason it's post-engineering, it's too precise I mean, it's so precise, it would never be used in any application. Too precise for any physical, real-world application. Real-world application. So just to put 10 to the minus 6 seems like, how are you supposed to wrap your head around 10 to the minus 6? For comparison, let's say you're trying to construct a road and you're going to make it a mile long. Okay, let's construct a 1 mile, exactly 1 mile road. Of course, there's no such thing as exactly. So how much of an error, let's say you get it right. If you get this right, to within the same computational accuracy as this student computed square root of 2 to within 10 to the minus 6 miles, how big is that? Well, how many miles in a foot? How many feet in a mile? 5,280? I think that's right. That's 5,280 feet. Let's see. Feet in mile. 5,280, beautiful. And so if I take that, so how many inches is that? 5,280 is how many inches in a foot? 12. So I just have to multiply this by 12. So 5,280 times 12 is 63,360. 63360 inches. So if I take that 63630 inches, so 10 to the minus 6 miles is 63,360 over 10 to the 6 inches. So let's work out what that is. 63, in fact, it's right here. Let's just do a new one. 63360 divided by 10 to the 6 is 0.06, is about 0.06 inches. You have made a mile of road, and you've measured that mile to within 6/100ths of an inch. That never happens. Today, it might with GPS that can get you, extreme precision. That does not happen in the world. The curvature of the Earth would get in the way of your calculation if you actually wanted to, get the line of sight from the start of the mile to the end of the mile. All right, that's what I mean by this 10 to the minus 6 is post-engineering. This is not something that's being used to measure something extremely accurately. It's way beyond what accurate measurement means in the real world. Okay, this is not the kind of precision we insist on almost any engineering task. But I call it pre-math. And the reason I call it pre-math is why? So this is why it's post-engineering. Why is it not yet math? Nargis. Exactly. There's no proof. So no unequivocal forever for the end of time proof that their accuracy is what they claim it is. Of no proof of claimed accuracy. So let's talk about this idea of proof. Okay. If you read chapter 1, how many of you read chapter 1? It's okay if you didn't. Okay, some of you read chapter 1. What's the earliest? So the earliest known to me, it might be known to some other people, and today, maybe in the future, I will know another instance. The earliest known mathematical proof, mathematical theorem, meaning a fact with a proof, is apparently due to Argus. Yes, Thales, I'm told by my Greek friends. I would call it Thales also. Thales or Thales. Thales of... Anybody know where he was from? Yeah. Thales of someplace. Good. Around when? Roughly? 600? Yeah, very roughly 600 BC. Okay, very roughly 600 BC. So in our grand picture here, we have fast forwarded. Oh, I didn't tell you when this Rhind papyrus is from. The Rhind papyrus is from about 1550 BC. The Moscow papyrus is from about 1850 BC. So these are things found, they're all Egyptian, they're Egyptian hieroglyph, and they're from around the same time as these Babylonian clay tablets. So over here we have the Rhind. Well, maybe Moscow is over here and Rhind is, I'll just go like that. Rhind is over here, Moscow is over here. And then the Pythagoreans are 550, just before the Pythagoreans, around 600 BC, is when we get our first theorem. This is Thales. Okay, so just to put everything in perspective. Here's what Thales was playing with, bless you. So here's what, where are we? Here's what Thales was playing with. In fact, let's do it in, this thing will draw better than I will. Let's go to GeoGebra. Okay. Have any of you heard of GeoGebra? GeoGebra is going to be your friend. Let me put it here. GeoGebra. Like geometry and algebra. GeoGebra.com.org. Okay. A lot of the geometry things that we'll be doing, if you want to draw like really nice circles really quickly, you just grab GeoGebra, there's a circle. Okay. So here's what Thales is playing with. I'm going to draw a diameter to this circle. There's a diameter. Let's put a point over here. Let me put a random point there. I'll put a point over here. Okay, random circle. I'm going to take the 3 points that I have, this diameter and this random point C, and I'm going to put them, I'm going to connect them into a triangle. Okay, so let's just write that down. Take a diameter to a circle and random point on the circle. So here's a circle, here's a diameter, and here's a random point. And what are we calling this? This is like the point C. Maybe this is A and B. And the question is, what is the measure of the angle at C? And you might say, Daniel, you want to tell us the answer? Danny? Yes, I was about to say, don't tell us the answer. Yeah, so erase that from the transcript, please. At the moment, the question seems ill-posed. How could you possibly know? Okay, except for Danny, how could you possibly know what this angle is? I haven't specified anything about this. In fact, I can drag, just to illustrate how ill-posed it seems, I can drag this point C anywhere on the circle. I haven't said anything about it. Okay, but Danny already told us, well, let's try to measure it. So here's how you measure an angle in GeoGebra. You say angle from D to C to B. Oh, D is called A in my picture. And indeed, I don't know if you can see that. Can you see that in the back? That says 90 degrees. I don't know how to make it bigger. Can I zoom in? No, that doesn't zoom the text. I don't want another point. I don't want another point. I just want to be able to pull things. So here it's at 90 degrees. There it's also at 90 degrees. There it's at 90 degrees. Why is this everywhere 90 degrees? So the fact that we have seen it, the fact that we've experienced, we've pulled it around, isn't that proof? We all see that this computer is measuring this angle and it's telling us that it's always 90 degrees. Danny said it's 90 degrees. Doesn't that count as a mathematical argument? So here's the theorem. I'm just going to say it. Theorem, the angle at C is equal to 90 degrees. In other words, a right angle. This is a right triangle. You can't not make a right triangle if you take the diameter of a circle and another point on the circle. As much as you try, that angle will be a right triangle, will be a right angle. Okay, we've all seen it. Isn't that evidence enough? So this goes a little bit into epistemology. Epistemology is the study of how do you know the things that you claim to know? How do you come to truth? How do you determine what is or isn't true? And actually, this is something that is different from culture to culture, even in modern times. If you have a civil suit in England, you know who you go before? You go before a suit is a jury of 12 peers, lay people off the street. Anybody know? You go before a tribunal. What's a tribunal? Let me write this word. Tribunal. Anybody know? In England? This is British common law, modern English common law.
I should know, but I don't.
It's 3 judges. Tribunal is 3 judges. 3 judges. You can't have one person determining everything. You need a little bit of checks and balances. So you have 3 people, 3 judges. By the way, tribunal does not come from tri, it comes from tribe. But tribe comes from 3 being infinity, as we discussed last time. Okay? It's like, I know my family, I know my mother, I know my sister, I know, my cousin, and then there's I can't keep track. It's infinitely many. It's tri. It's 3. Once there's 3 families, now we're a tribe, and a tribunal comes from tribe, and a tribunal consists of 3 judges. When you have a civil lawsuit in England, you have 3 judges, 3 experts on determining facts. 3 judges are experts on determining which facts are true or not, which facts are true. Now, the way they go about determining is the same way that we have in our systems. There's a prosecutor, there's a defense, there's attorneys who help people make their case. They present evidence. The evidence could be physical evidence or testimony or expert testimony. So there's experts in whatever fact they're trying to establish. An expert will come, but it's up to those 3 judges to determine which experts they believe and which experts they do not. Even today, we have completely different methods of epistemology, determining facts. What is it in the US? Jury. We already said it's a jury. The facts are determined by the jury. What is the judge doing? Sometimes judges are involved in sentencing, yes, but just in the court itself.
What's the jury?
Recording the jury, yeah, but the jury said, we the jury find the defendant guilty or not guilty, right? We the jury are making this determination based on the facts that we believe. The facts are the prosecution is presenting one set of facts that they claim means that the person is guilty. The defense is presenting another set of facts that they claim means the person is innocent. And we find the defendant guilty. By the way, it's not innocent. You're already innocent, right? You're assumed innocent. It's guilty or not guilty. You may still be guilty. We just can't find you guilty. So we find you not guilty. Nargis. Exactly. The jury determines facts. Lay people off the street are who the founders of this country decided should be determining what the facts are. The judge is an expert on the law. Judge is an expert on law, making sure that in the courtroom, everything that's being done is following rules and regulations, what it means for someone to be tried. Okay, so the judge is the expert on the law, not on the facts. Lay people are experts on the facts. Every single individual, man, woman off the street, is who is going to determine which experts they believe, they trust. And this system obviously has its flaws. The 3 judges system have their flaws. There's no such thing as a perfect system that will every single time make the right call. The question is, what do we believe is the best mechanism by which to make as few mistakes as possible? In the US, we decided we want jury of our peers. In England, there's still, actually, I think in criminal law in England, they do have juries. I don't know when that switched over. Someone can research that and educate me. Allison. We don't yet know that. So C, we observed it. We have empirical evidence. We have looks like a ton of empirical evidence that C seems to be 90 degrees regardless of where C is, but we don't yet have as a proof. And before I give you the proof, what I want to explain to you is I'm a judge in the sense of the US, not in the sense of England. Each of you is responsible for determining the truth for yourselves. I can guide you to what I think is the truth. But you at the end, there's something called a bar mitzvah, right? What's a bar mitzvah? Why do Jewish kids a party and you try to like dance with a girl or something, like what is the purpose of a bar mitzvah? Turning into adult, yes, it's some kind of, you're going through puberty and so on, but like, what do? You read from the Torah. Why? Why are you required? Every single person is required to read from the Torah. The Torah is the primary source of law, and you're required to demonstrate your ability in front of a congregation to read. You yourself can read those words. You have a rabbi, the rabbi guides you, but you yourself are required to know what's there. You're responsible. Each individual is responsible for being able to at least have access to the primary source and make their own decisions, right? So that's, by the way, Israel means wrestling with, El is God. Israel is wrestling with God. You must yourself be able to argue against God, fight against God. So, okay, anyway. So let's prove this. So in mathematics, we follow the US system. Every individual must, when I give a proof, it's not me, the judge, telling you what's going on. I'm recommending things to you. I'm following the laws of logic. Hopefully I don't need to give you the laws of logic. We all intuitively will figure them out. But the question of whether my argument is satisfactory to you is determined by each of you individually. Does that make sense? That's what I mean by please argue with me if you don't understand something. If at the end of the day, if at the end of this proof, you still don't understand why that angle must be C and must forever be C, and how we can prove infinitely many facts all at once, regardless of where C is, proving infinitely many things with a rigorous argument. Okay, does that make sense? Okay, so let's again, just to have it here, state Thales' theorem. Thales' theorem. Thales' theorem. If AB is a diameter of a circle. Here's a circle. Here's AB is a diameter. And C is on the circle somewhere, anywhere. Then the angle at C, or if you want to be more precise, the angle from A to C to B. This is the angle from A to C to B. I'm sorry to those of you who are having heart palpitations because high school geometry is coming back. We're going to be doing a bit of this, but it's going to be all very elementary. So, you know, we're going to keep it down. This angle measures 90 degrees. They wouldn't call it 90 degrees. They would say a right angle. We know that it's 90 degrees. This is going to be a right angle. Proof, demonstration. Why is this true? Okay, Yuri's got the key idea. How did you know that you know this proof already, or you read it in the book, or you just kind of see what to do? It's easy enough. Great. For Yuri, it's easy enough. For other people, it might take thousands of years to figure out, for humanity to come to the conclusion and it's not the only way you can prove this theorem, but Yuri had a brilliant idea. There's something that's not on this picture that would make the argument much easier if we had on this picture. So Yuri's idea, and this is what I mean by ideas are crucial. Ideas are essential. Mathematicians live and breathe by ideas. The idea is draw the circle from the segment from O to C, where O is typically denoted as the center of the circle. So here's O, and Yuri says, draw a line segment from O to C. I don't know how Yuri came up with that. I don't know how you would come up with it. I don't know how Thales would come up with it. But it's just something that comes into people's heads. Ideas just come into people's heads. That's the amazing thing about them. If I knew how they came into people's heads, I would try to gain that and get more ideas into my head, and it would help me with the problems I'm trying to solve. So what? The ideas, I can't say this in mixed company. Ideas are, everyone has them and they all stink. Most ideas are wrong. The vast majority of ideas that you have about things don't work out. The reason we have nice things, computers and rooms, and the reason we're not out in the wilderness picking berries off trees is because people keep trying things. And 99% of the things that people try don't work, but we keep trying anyway. And we keep having this thing where we try things that don't work, we try something else that doesn't work, we try something else that doesn't work. 1 out of 1,000 ideas might actually work. And when you compound that, you get to our modern existence. We're here as a result of thousands of people, millions, billions of people having trillions of ideas, of which 99.999 didn't work. This idea does work. Let's see why. Okay, so say that again. OA is a radius of the circle. So let's write that down. OA is a radius. So is OB. That radius is half the diameter. So is OB. And so is OC. That's what it means for A, B, and C to be on a circle, is they're all equidistant from the center of that circle. So OA, OB, and OC are all on this circle. Interesting. So what? Okay, so slow down a little bit. So here's what Yuri's saying. Let's look at triangle OAC. I just want to isolate this one little triangle, OAC. Okay, look at the triangle OAC. So I'll just redraw it here. This is O, this is A, this is C. And what we just said above is that OA and OC are equal. Isosceles. This triangle is isosceles. Isosceles, same sides. Two sides are the same. Isosceles. Isosceles. So what, Nargis? Exactly. There's a mirror symmetry. There's a mirror symmetry. Now, each of the, okay, I'm getting a little bit ahead of myself, but every single thing that we're saying, you guys keep saying, oh, look, these things are equal, and equal things have to be equal to other things, and so this angle is equal to that angle. We're using other knowledge to build on top of this knowledge. But let's come back to that. Let's say that we now understand that there's a mirror symmetry. That means that angle A is equal to angle C. Let's give it a name. Let's call it alpha or something. Okay, so the angle, and by the way, I can't just say angle A because now there are several angles at A. There's actually I can say angle A, but I can't say angle C because there's now three different things that angle at C could mean. It could mean BCO, it could mean OCA, it could mean BCA, so we have to be a little bit more precise. So when I say here angle A, let's specify what these angles are, really. The angle from O to A to C, O to A to C, is the same as the angle from O to C to A, O to C to A, exactly by this mirror symmetry. Okay, and we're going to call this thing alpha, alpha. So where is that in our original diagram? Here's OAC. This angle is alpha, and this little bit of angle is alpha. Great. Any other ideas? I guess there's the same thing for OBC. OBC is also isosceles. Similarly, triangle OBC is isosceles. And so, well, I'll just draw it here so that we have the references OBC, with OB and OC being the two equal sides. I don't know what the angle at B is. Let's give it another name. Beta, as good a name as any. So the angle at OBC is equal to the angle at OCB. If I go the other way, these angles are the same, and let's call that beta. Beta. So up here, let me slow down. People are still writing. Everybody with me so far? Did I lose anybody? The heart palpitations have stopped. We're okay. No bad flashbacks. So the triangle OBC is over here, and I'm saying that that angle I'm going to say is beta. Obviously, alpha and beta change as C sweeps around. Alpha and beta are going all over the place. This is the angle beta. Great, I like it. So what? This right now, the silence, that's mathematics. The looking for an idea. Yuri's got another idea, but I want to just hold her a little bit before live in this space of ignorance. This is my entire existence. This space of silence and like, what the hell do I do now? That's my career. My career is sitting around waiting for an idea to come. I go for a walk, I have some tea, I talk to a colleague, I read a journal, I read a newspaper. I'm waiting for something to happen. Jemima. Most ideas are wrong. We still have to come up with them. We have to generate. The more ideas you generate, the more chance you have something that works. Jemima. Why? Fascinating. Fascinating. So Jemima has another idea. Here's a crazy idea, which again relies itself on prior knowledge, just like the fact that the two sides, if a triangle is isosceles, then the two base angles are equal. That's prior knowledge. You know, this fact itself needs establishment. Fact needs to be established. Needs to be established. Oh God. My handwriting is bad, but it's should I slow down and try to write neater, or you guys can handle it? You can handle it. This fact needs to be established. So here's another. Jemima's got another idea that she wants to toss into the mix. This theorem is really getting juicy. It's not a one and done. We need another idea. And the other idea is that the sum of angles in a triangle adds up to what we would call 180 degrees, what they would call two right angles. 180 degrees. How did you know that? Well, you just knew that because you're in the West. So again, this itself requires proof, but let's just move on, because if we went back to every single thing, we'd be here all day, and we will be here all day in a mathematical sense. So this is another fact that needs to be established. But let's say you know that fact. Jemima looks back at this triangle and she says, look at triangle ABC. We've got alpha, and this is alpha plus beta, and we've got beta. I'm going to redraw triangle ABC down here. Here's triangle ABC. Whatever it is, there's some other angle here. It doesn't even matter what's going on. This side is alpha. That side is also alpha. This side is beta. That side is also beta. So the sum of all of the angles in this triangle, the angle at A plus the angle at B, oh, I called it beta, but that's good, actually. That works. Plus the angle at C has to be 180. The angle at A is alpha. The angle at B is, everybody see that? The angle at B is beta. The angle at C has alpha plus beta. Alpha plus beta. Does everybody see that? Which is 2 alpha plus 2 beta, or 2 times alpha plus beta. Well, if twice alpha beta is 180, then alpha beta itself, twice alpha plus beta is 180, then alpha plus beta itself is 90. And alpha plus beta itself is exactly the measure of the angle at C. And that is a proof. So we write quid erat demonstratum, as was to be demonstrated. That's our first actual theorem. And historically, at least as far as I know, and as far as I know today, that's the first theorem known to mankind that survived antiquity. Amelia. I'm sorry. Yeah, right. No, don't tell me. No, tell me. Jillian. Thank you, Jillian.
So I'm curious because we did this using a lot of prior knowledge.
Yes.
How was this done?
It was done using a lot of prior knowledge. And this goes to, I guess we can go there now. This goes to a very fundamental thing, which was finally worked out shortly thereafter by the Pythagoreans. Jillian is bringing up an amazing point. If all mathematics is going to require some kind of prior knowledge, because any fact that you want to establish is going to rely on some other fact that needs to be established, and that's going to rely on some other facts that need to be established. So you have this infinite recursion of, to establish some facts, we need other facts. And those facts need facts for them to be established. And they need to be established. And they need to be established. And they need to be established. And so on forever. That means we can't actually ever get anywhere. Yes, Mary. Yes. And he calls them? Yes, exactly. So about half, oh, sorry, continue. We're going to have an entire week, if not more, devoted to that.
The practicality of just going ahead and establishing some things as self-evident, and then using that to move on to establish your proofs.
Yeah. And that idea of axiomatizing things is, what's the Declaration of Independence? We hold these truths to be self-evident. That idea permeates our notion of, so it's something that you immediately face when you face this proof. Jillian brought it right up. How do we know those facts? We're going to need to prove those facts in terms of other facts. And Mary says, we need axioms. So this is what the Pythagoreans, only 50 years, Thales is 600 BC. Pythagoras, who knows if there really was a person named Pythagoras? There certainly was at least a cult called the Pythagoreans, maybe led by Pythagoras. Who knows? At least I don't know. If you guys know better, please educate me. So starting, this is like around 550 BC, make the leap from we need to prove things to we need to have axioms. We need to have So we've made two leaps, by the way. Let me write it down and then I'll point out the two leaps. Need to have, need to hold certain truths self-evident without justification. Need to have axioms. So, quote unquote, self-evident, although they're not at all self-evident, as we'll discuss, as Mary pointed out when we get to Euclid, self-evident, bless you, truths. We've made, let's pause for 1 second and notice the two massive leaps in our understanding of mathematics that we made just in these two steps. We went from, leap from truths, facts that you establish as true. This is already in YBC, in the Babylonian clay tablets and the Rhynd papyrus, to a pair, truth, plus a proof of that truth. That's Thales. That's a first attempt at that. To the Pythagoreans, very soon thereafter, a triplet of truth needs to come with a set of axioms, things that we will not justify, so that we can stop this ungodly recursion. There's not going to be an infinite recursion. This is where we start. These are the axioms from which we're going to work. And proof. Given those axioms, we'll follow Thales's tradition and add proof. So these are massive leaps in the epistemological understanding of mathematics of humanity. Human beings are really, this is a change in mathematics. This begins with the Pythagoreans. All right, we have 3 minutes. Let me tell you one of the axioms of the Pythagoreans, and we're going to pick up here next time. So here's a Pythagorean axiom. Pythagorean axiom. It's called the axiom of, the technical term is axiom of commensurability. Commensurability. Here's the axiom. Given two sticks, here's what I want you to do. So here's one stick, and here's another stick. You take two sticks off the ground, you line them up, and you break the longer one where it sticks out. Where it sticks out. Okay, so you break the longer one right there. And now you have two sticks. Well, two of the sticks are exactly equal. So you have two sticks. You have the original stick, and now you have this new stick. So now I'm just going to move this new stick over there. So here's that new stick. And you do it again. Do it again. So I'm going to break the larger stick by the size of the smaller stick. And I'm left over with this stick. Actually, this stick is still larger. So maybe I'll put that one in between just so that we can continue the process. Does everybody see what I'm doing? Maybe if I color these, it'll be a little easier to see. Where's the, oh, here we are. Okay. So this little red, please. Pretty, please. Pretty, please. That's what works. So here's the red one. And this is still the red one. What am I doing? Let's make this one green. Do you guys see what I'm doing? This stick is green. The green stick has been moved over to here. This is so embarrassing. How am I getting this wrong? I'm not going to try to color it. That's the way to do it. I think it's clear what's going on already. You take two sticks, you break the longer one, you break the longer one by the length of the shorter one, and you get a new stick. That new stick goes over here, you break that off of there, that's a new stick. The only thing I want to color is this little length has been moved over here. Okay, and this original length is what I want to do. And this original length is the same as this. But I'm glad this is the end. We're going to pick up here next time. Okay, and here's the axiom. So you do it again until you stop. And when you stop is when you have two little sticks that are exactly the same size. So maybe we break it here, and then this little stick measures the other stick 3 or 4 times. And now you have you have one little stick. So really what the axiom says is, here's the true axiom. Given two sticks, there always exists a smaller stick that measures both. That measures both evenly. Okay? We're going to explore evenly. We're going to explore the consequences of this axiom to geometry. So again, the Pythagoreans have added, we're going to go over this next time, but they've added that you need not just a truth and a proof, but a truth, axioms, and a proof. And this was an axiom that they began working all of their geometry with. Which word can't you tell, Jillian? Commensurability. Here, anything that actually needs to be understood should be typed. Commensurability. Axiom of commensurability.